How Machine Learning Works, an intro to gradient descent in JavaScript with Matt Dupree.
So this is Mighty Mouse. I don't know how many people are familiar with Mighty Mouse. I grew up on cartoons, and so I was a big fan of Mighty Mouse coming up. Obviously, the premise is that there's this mouse, but it's mighty, so it's small, but it can do amazing things. And when I was thinking about a way of introducing gradient descent, Mighty Mouse kind of came to mind as a metaphor because it's small, but the algorithm, it's small, but it can do amazing things. So let me kind of say a little more about that to show you what I mean. So does anybody know what this is? Does anybody recognize this? Feel free to just throw an answer in the chat. If you recognize, I mean, this is a data set. It's a fairly well-known one if you've looked at some machine learning problems. Anybody have any ideas? Looking at the chat here to see if anybody. Yes, Jen, awesome. Okay, yeah. So yeah, the matrix is a good guess. Yeah, so MNIST is right. That's the name of a data set. It's handwritten digits that are used for the handwriting recognition task. And this is a very basic kind of deep learning task. And this task uses gradient descent. So on one end of the spectrum, like a kind of a very basic deep learning task, you have this task that uses gradient descent. And then on the other end of the spectrum, there's a project that creates like some really cutting edge stuff, which is, this is actually something that somebody's done with GPT-3 recently. And what this does is it actually generates code based on a natural language description of a UI element. I don't know if you've seen this on Twitter. It's about maybe 3 or 4 weeks old now. So this is like very cutting edge deep learning stuff. Also uses gradient descent. Again, like it's a small but kind of mighty algorithm that is important in a variety of deep learning tasks. And just to give you an idea of how small it is, you can actually implement it on like a toy problem in just like 20 lines of code. So this is the entirety of gradient descent for the toy problem that we're going to be interested in for this session. We're not going to do anything as sophisticated as generating code from natural language descriptions of UI elements, but we are going to implement gradient descent for a simple problem. And the problem that we're going to be interested in is the problem of predicting video game sales based on Metacritic scores. So Fortnite's been, kind of being discussed lately because of what's happened in the App Store. So I figured that'd be a fun example. But with Fortnite, you have, Metacritic scores, and then you also have like the number of users or downloads for the game. And there is some sort of relationship between the Metacritic score, the user score, and the actual number of users and downloads that the game receives. So what we're interested in is basically creating a function that predicts global sales given Metacritic score. And we're going to create that function using machine learning and gradient descent. Now, this isn't really like a deep learning problem. It's a simple, really linear regression thing. But the algorithm that we're using, gradient descent, is going to be it's the algorithm that's really key to a lot of machine learning problems. So let's actually start by writing some code. Okay. So let's really quickly talk about the shape of the data. So I've already set things up so that I basically have a CSV file that has a bunch of video games and like their sales and Metacritic score. And so the data that I'm getting here, I'm just using like a simple node CSV parsing library. But the data that's returned here is it's an array of objects that are basically global sales. It's a number, and then the Metacritic score, which is also a number. So that's what our data looks like. I actually might be misremembering this key, so I'm going to look at this file for a second to make sure. It's just critic score, not Metacritic score. So that's the actual shape of our data. And what we just said is we want to create a function that can predict the global sales given the Metacritic score. So we're going to go ahead and create that function, and so we're going to use a higher order function here. Make model. Model is just a way of talking about this function that we're making that maps from critic score to global sales, and it's going to take in, like we said, critic score, and it's going to return an estimate of global sales. We're just going to put in 0 for now. All right, so this is like, and it's going to take in some data. So based on our training data, based on our training data, we're going to return a function that can predict global sales from Metacritic score. So we're just kind of putting some scaffolding here and writing kind of the signature of the function that we're interested in. So let's jump back to the slides. And let's look at, if we wanted to solve this problem like without machine learning, without anything fancy, what we might do is just plot the Metacritic score versus global sales. And so if we did this in like Excel or R or Matplotlib or something like that, this is the plot that we would see. And hopefully you guys can see my cursor here, but you can tell that there is some sort of statistical relationship between the critic score and the global sales. So your critic score is on the x-axis, and then your sales is on the y-axis. So you can see that there are more of these points for higher sales when the critic score is higher. And if you were, again, using Excel, you might just like draw a line of best fit. And that's like, you're doing like some rudimentary machine learning there, right? And with that line of best fit, you can actually use that to make a prediction about what your global sales will be based on critic score. So, right at 75 here, this line of best fit is telling us that, like, all right, we should predict, I guess that would be maybe like 1 million global sales here. So, yeah, that's how we could solve this, just using Excel. And this is just to kind of orient, what we're doing here and make it a little more concrete. So we know from like high school algebra that the equation for this line is, y equals mx plus b, where m is the slope and b is the intercept. Now, if we go back here, we see that this intercept is negative. That's kind of nonsense because like we would never predict that the global sales for a game would be less than 0. But so there's like the intercept here is a little silly, but we at least know that the equation of this line here. So the intercept is like is mathematically meaningful, but it doesn't necessarily mean anything for this data set, the way things are set up. So again, like y here is sales and x is the critic score. So the question is, so if we think about that line of best fit, the values that we saw for the slope were 0.0253 and negative 1.1406. So those are the correct values for M and B. So let's update our code to kind of reflect our current understanding of the problem here. So we know that this function here, it's going to be concerned with M and B. So we're going to start off by just initializing those values to 0. Oops. And now our function is actually going to return not just our predictor function, but also the values for M and B. So when we actually want to call this, we'll pass in our data, and then we'll destructure to get M and B and our predict function. Okay, great. So really quickly, let's just run this to make sure. Everything's working. Okay, great. So that's reasonable. We initialize these values to 0, and we haven't done anything with them, so that's what we expect. Great. So let's jump back to our slides. So we know that this is the correct value of M and B, but the question is, like, how do we figure out how do we go from a guess of 0 to the correct values? So we're starting out with 0, like we were saying, and we need to figure out how to get to the correct values. Now, what we need in order to do this is an objective way of assessing how good our guesses are for M and B. And so what would that, like, how could we actually do that? So in order to see that, we're going to look at this example plot. And if we have M and B as 0, what would that look like if we drew that on this plot? So we have the scatter plot here. If we drew a line of best fit where M and B are 0, what is that going to look like? Go ahead and throw it in the chat. Any guesses? All right, I'm gonna move on. So it's just gonna be a flat line. So if the slope is 0 and the intercept is 0, then yep, there it is. Awesome. There's a little bit of lag there, I guess. Great. So if we're guessing 0, that's what our line's going to look like. And if we wanted to assess how good of a line of best fit this is, then what we can do is we can measure the distance between our line of best fit and the points on the plot. And then what we can do is we can basically sum up these distances and average them. So that's going to give us a measure of how good our guess is for M and B. Now, to see this, if you contrast that line of best fit with a line of best fit that's actually good, then you're going to wind up with, I'm seeing, could we, so 1 second, it looks like some people are having a hard time seeing. So it says, could we?
Yeah, there's no way for me to rearrange these windows. I think sometimes some of the stuff gets covered in the bottom left corner of the screen.
Oh, in the bottom left? All right, I'll try and be more cognizant of that. All right, so if we have a better line of best fit here, if we, again, take the distance between our line of best fit and the points on the scatter plot and then average those up, average up the sum of the distances, then we're going to wind up with a smaller value here, which suggests that our line of best fit is actually better. Or rather, it suggests that our values for M and B are better. And so that's how we can kind of objectively assess how good our guesses are for M and B. So what we've just kind of shown here intuitively, visually, is something called a cost function. And like, here's the kind of mathematical symbols for what we just described. So we're going to go ahead and implement this in code. I wouldn't worry too much about like whether this mathematical expression makes sense. But right now, it might make more sense once we implement it in code. And so that's what we're going to do really quickly. So let's do that. All right. So I'm going to a thing called compute cost. Oops. It's going to take in MB and data. And I bet we can do this in one line, but so we're just going to reduce on our array of data. And let me just it's out. So we're going to start at 0. Our cost starts at 0, and we're going to divide by the length of the data, the number of data points. And, okay. So what we're going to be doing here is we want to calculate the difference between the predicted value and the actual value. Which is basically the distance between our line of best fit and the actual point on the plot that we saw earlier. Let me close this. Hopefully people can see that better. I know the bottom left is not great. So, all right, so what we're going to do is we will calculate that difference. So we will do m, do parentheses, m times the, oh, actually, I need to destructure on this. So what we have here, each element in the data array, like I was saying earlier, is global sales. It's an object that has global sales and critic score. And so what we're going to do is we're going to say our equation here is y equals mx plus b. So we're going to do m times critic score plus b. And we're going to subtract that from the actual global sales from the data set. And then we need to square the difference between these things. So we'll do this. It looks like Prettier is just stripping the parentheses here. But yeah, that should get us a function that computes the cost of our guesses of M and B. So really quickly to test that, I'm just going to call compute cost with zeros as M and B and the data. I'm going to log that out. This is just to test our cost function. And then I'm going to call it again with the correct values of M and B. And what we should see here is that the cost with the correct values of M and B is going to be lower. And that'll tell us that we actually implemented this correctly. So let's pop up a terminal again. And it's unfortunate that you can't see the results on the terminal. Okay, so we have an unexpected token. What did I do here? Oh, okay. So I need to, first of all, I need to, somebody trying to help me out with line 29. So first of all, I need to return here. Let's start, and then line 29. Oh, yeah. Yeah, what happened there? That's weird. Okay. Good. So 2 mistakes there. Okay, great. So so far these results look same. So I don't know if you can see this, but the first the cost of using the value 0, 0 for M and B is 1.399, and the cost of using the correct values for M and B is 0.91. So it is lower, which is great. That's what we want to see. We want to see that the cost is lower as we use more correct values for M and B. So that's great. So we've implemented the cost function, and hopefully that that helps to solidify our understanding of that mathematical formula that we threw up on the screen earlier. So let's go back to this. And if we look at this mathematical formula, the only variables here are M and B. Everything else is actually filled in by our data set. So if you look at like X sub I, that's the Metacritic score for a particular video game, and Y sub I is the global sales for a particular video game, and N is the number of values in the data set. So M and B are really the only variables here, and those are the things that we're trying to figure out. So we can kind of rewrite this cost function and kind of highlight that, you know, this is a function of the variables M and B. So now that we've clarified that, let's see here. I think I've already done this part of the code, so I'm gonna move on. Great. So what we're gonna do is we're gonna ignore one of the variables of this equation for a second. We're just going to think about the cost function as a function of M, like the slope that we're trying to figure out, and we're going to get rid of B. So if we ignore that and we look at, spoiler alert a little bit there. This is what I get for not using my notes. So if we think about what this function is a function of, it's basically a quadratic function, right? The only variable here is M, and there's some other stuff around M that's kind of transforming it a little bit, but it's a quadratic function. So what what does a quadratic function look like if we graph it? And I kind of gave you the answer when I flashed the slide up there. So, but yeah, if you want to give the answer in the chat, I'd love to see it. Yeah, boom, parabola. That's exactly right. Okay, great. So let's say that our guess for m being 0 is to the right. Actually, yeah, it's to the right. And actually, let me clarify before I ask this question. So on the y-axis here, we have the cost of the cost function as a result of choosing different values of m. So the x-axis is m, and the y-axis is the cost. Now, we know that we're interested in minimizing the cost. Minimizing the cost is going to give us good values for m and b. And so if we graph the cost as a function of m, and we wind up with this parabola, and we know that m is a little bit far to the right. Does anybody have a guess? This is a hard question. Does anybody have an idea of how we could figure out mathematically which direction we need to move in order to adjust our value of m? So how could we figure out mathematically whether m is too positive or too negative? So I'll ask that, and then I'll give a hint that isn't giving the answer if nobody can figure it out. So I'll wait like 10 seconds. Okay, so here's your hint. So think about why the algorithm, yes, wow, that's really great. So yeah, somebody recommended taking a derivative. So the hint I was gonna say is like, think about why the algorithm might be called gradient descent. So yeah, the derivative is involved here. So if you think about what happens if we take the derivative at this point, when we take the derivative at this point, if you're not familiar with derivatives, like you can think of it as just the slope at a certain point. So the slope of the tangent line at this point is positive. And so if you take your original guess and you subtract the derivative from that, that's going to move you in a more negative direction. So because the derivative here is positive and you subtract that away, that's going to move you in a more negative direction, which is closer towards the bottom of that parabola, which is exactly what you want. You want to be at the bottom of the parabola where your cost is low. That tells you that your value for m is actually going to give you a good line of best fit. The same logic applies if your m value is too far to the left of the minimum. So if you take the derivative here, the slope is actually going to be negative. And if you subtract that from your initial guess of m, if you subtract the negative thing, you're adding it. And so that's going to move you to the right, closer to this minimum that you're interested in getting to. So the reason that this algorithm is called gradient descent is you're basically taking derivatives and using that to descend down the parabola. So hopefully that helps like shed some light on just the naming of the algorithm and also how it works. So let's actually, in order to like think about the derivative, let's look again at this cost function. And again, don't worry too much about like the calculus here, how we actually, oh, okay, I see a question. Why are we trying to get to the minimum? Yeah, so that's a good question. So the minimum, the reason we're trying to get to the minimum is a low cost is a way of basically objectively measuring that our values for m and b are good values. They're actually going to be an optimal slope and intercept for the line of best fit. So Jerry's trying to help out there, I think, a little bit. So we can actually go over that a little bit towards the end. We can review that, but yeah, you want to minimize the cost function in order to find the best values for m and b. So we're going to really quickly walk through taking the derivative of these things, and you're actually going to be doing some partial derivatives here. Again, don't worry about it too much if the calculus is a little rusty. So I'm just going to rewrite this equation and replace cost with j, and then I'm just showing here the partial derivative of j with respect to m, the slope parameter. And this is the actual value of the derivative. It's roughly the value of the partial derivative. I'm ignoring constants and stuff, and it's good enough for us to work with here. So this is roughly the value that we're interested in. So does anybody have any questions at this point? Getify, I'm sorry, I'm sure that's not your actual name. So this might be an opportunity for you to ask any follow-ups if you didn't feel that I'd answered it before. If you don't understand this yet, we're going to walk through the same things with B. So we did everything with M just now. We're going to do everything with B, and you'll basically get to see this again. But if there are any questions before we move on, then go ahead and ask them. All right, I'm going to keep moving. All right, so let's write some code to actually apply this this derivative here. So we're going to go back up to our make model function, and we know that we need to update m in accordance with this derivative that we're calculating. So let's calculate the derivative for m. So I'm going to store this in a variable called m grad for m gradient. And again, we're going to reduce here. And we know that reduce takes an accumulator and a current value. I'm just going to do 0 for now and make sure that our initial value is 0, and also make sure that we divide by the number of data points in the data set, because that comes from our formula. Now I want to actually fill in this part. So we know that we're just going to be adding things to the accumulator. And we know that basically the derivative here is going to be n times critic score. Oh, whoops, I forgot about destructuring again. So let's global sales. Okay, so we're going to multiply by our critic score, and then we're going to add e there, and we're taking the difference between that and global sales, and then we're multiplying that by the critic score. So, okay, prettier stripping the parentheses again, but so let me just check the formula again to make sure that that is correct. So, yep, we're taking basically the difference between our prediction and the actual value and multiplying it by x. And it looks like the difference between our prediction and the actual value and multiplying it by x, which is the critic score. Yep, that looks right. So now what I'm going to do is we need to subtract the gradient. So I'm going to update the value for m based on the gradient that we just calculated. Okay, great. So let's walk through. Oh, great. I see a question. Is cost the inaccuracy of the guess? Yeah, that's a pretty good way of thinking about it. So the higher the cost, the more inaccurate your guess is for M and B. So that's why you want to minimize it. Okay, so let's really quickly walk through this again with B to help solidify what we just did here. So all the logic that we just kind of went through about how to improve our guesses for M and B, the same logic applies for B as it does for M. So we basically start with M and switch this out with B. And again, if your guess for B is too far on the positive side, the slope is going to be positive when you take the derivative. And so that's going to move you in the right direction. So this is our cost function again. And if we take the derivative with respect to B, this is roughly what we wind up with. And so we can really quickly implement this in code. This is actually even simpler to do. So, we're going to do oh, I forgot to return here. So, all right, so again, we're going to do a reduce on all of our data. I'm going to restructure here. Okay, so similar story here, and what we're doing is we're returning, we're just basically splitting up over everything in the data set. It's basically just the difference between our prediction and the actual value, and that gets us the B gradient value. I must have accidentally deleted my update for M. We're going to do the same update for B. And okay, great. So, oh, whoops, that's where it went. And this is not perfection. Okay, thanks for calling that out. Yeah, line 18. Okay, great. So let's just double check the formula to make sure that's right. Yeah, this is just the difference, the average difference between our predicted value and the actual value. That's the gradient for the B parameter. Okay, great. So let's go back to our slides. And okay, so is there a reason to divide by, sorry, I'm looking at a question here. Is there a reason to divide by the data.length? Isn't that fixed for the data set? Okay, so the reason to divide by data.length is it relates to how we're thinking about the cost of, how we're thinking about the cost function. So if we look at the formula here, we're basically taking the average of the squared difference between our prediction and the actual value. And so in order to take that average, we need to divide by the number of data points, which is why we're dividing by data.length. It is going to be fixed for the data set. So I guess maybe what you're suggesting is I extract that into like a variable. You know, I could do like, I could do this, and instead of repeating myself here, I could just divide by num points. That's something that we could do here. But yeah, it is fixed for the data set. Okay, so that's that. Right. So what we just implemented in code is basically taking, oh, whoops. So what we just implemented in code is basically taking one step in the right direction towards this minimum. But what we actually need to do is take multiple steps until we wind up at the minimum. And you know, at the minimum, the derivative of is going to be 0, right? And so we need to basically throw this these gradient descent steps into a loop. And how many times are we going to need to execute that loop? Well, I happen to know that it's about 1 million times for this data set. And this is something called a hyperparameter. If you've ever heard people talk about this in machine learning, this is like, it's a parameter of the algorithm that you kind of just have to play around with and see how it affects your results. So, but let's go ahead and put this into our code. So our make model function is going to take in a number of iterations now. And what we're going to do is we're going to go ahead and throw all of this into a for loop. And let's move this. Okay. All right, great. So so now we are taking, we're going to update M and B 1 million times. And actually, I need to update the call site here with 1 million. Yes, that's 1 million. Great. So that's another update that we made to the code. Now let's jump back to our slides. And let's consider a problem with the algorithm that we haven't really talked about so far. So what would happen if, so let's back up a second. So with the gradient, with the derivatives, that basically tells us in which direction we need to move our guess for M and B. But it doesn't tell us how big of a step we need to take down this parabola. So what would happen, what would happen if we took too big of a step down this gradient, or down this parabola here? Does anybody want to guess what would happen to our algorithm? All right, so derivative change sign. Yeah, that would happen, but let's look at it visually. So if we take too big of a step, what we're going to do is we're going to overshoot our minimum, and then the derivative will change side, and then we move back to the other direction, but we're still going to overshoot the minimum. And basically we're going to, yep, it's not going to converge. Exactly. We're going to bounce out of this parabola, and we're never going to reach the minimum here and arrive at good values for M and B. And the way that that's addressed in gradient descent is another hyperparameter called the learning rate. So right now, the way that our code works is we basically have a learning rate of 1. We're taking a step that's not scaling the derivative at all to shrink the type of step that we're making. So like, we're taking that, that step of 1, and really we might need something like 0.1, where we're just taking a smaller step down the gradient. So I happen to know that the learning rate that's useful for this data set is 0.003. So right now our learning rate is 1, which is way too high, and so we're not actually going to arrive at useful values of M and B. So let's update our code to reflect this. So we're going to take in the learning rate now as another parameter, and we're going to scale our steps by the learning rate. And we just need to update the call site to pass in 3. Great. Okay. So, all right, so we are here. This is what I said at the beginning, that like we can fit this algorithm in about 20 lines of code. It's done. Let's see if it works. I mean, we can compare kind of this slide with the code that we have here. So here's the code. It's about 22 lines, I guess, with white space. There is this compute cost thing that we did, but that's not, strictly speaking, a part of the gradient descent algorithm. It's something that we're actually going to use for debugging, and just it's something that we did to kind of solidify our understanding of the concepts. So what we're going to do is we're going to just run 10 steps of this gradient descent, and we're going to make sure that M and B are moving in the correct direction. So what we're going to do is log out the values for M and B, and let's run this. Okay, so this is good. So our initial values for M and B were 0. And we know that the correct value is 0.0253 for M and negative 1.1406 for B. So we see here, you might not be able to see this because it's in the bottom left, but after 10 iterations, we see that M is moving in the correct direction, the positive direction, towards 0.02, and B is moving in the negative direction towards that negative 1.1406. So this tells us that our algorithm is actually adjusting M and B to reasonable values that are actually the correct values when we do a line of best fit. So let's get rid of, actually we'll keep logging M and B, and then we'll add to that a log of a prediction. So we will predict the global sales for a game with Metacritic score 80 based on our data set. And I'm going to go ahead and remove this. I'll actually have this run for 1 million iterations. And then let's run this and confirm that we get the correct values for M and B, and that we get like a reasonable result when we run this prediction. So this is going to take about 2 minutes. That's going to give us some opportunity to address any additional questions I will say that there's something that you're supposed to do to your data to make gradient descent run faster that we haven't done, just because I didn't really have the time to cover it. But ordinarily, like, gradient descent shouldn't take this long on such a simple model with like such a small amount of data points. But because we didn't do some of the pre-processing, that's why it's taking this amount of time. Okay, so we probably have about 90 seconds for any questions that anybody has. And hopefully, at the end of the 90 seconds, we'll have answered questions, and this will just spit out the correct values, and the demo gods will have smiled upon me. If you have any questions, go ahead and throw them in the chat. While I'm waiting for questions, I'm going to just look at the code just in case there's anything that I missed. Yeah, okay, so Jerry has a question about what pre-processing of the data would help. So that's a good question. So the pre-processing that you're going to want to do, basically, you would basically normalize the data. So you are, actually, let me go back to a slide here to kind of explain what the normalization does. I'm not going to get into the details of exactly what the normalization is, but let's actually just see if we can find a clean parabola here without anything else. Oh yeah, we can. Okay, whatever. So what the normalization does is it gives you a steeper parabola. And when you have a steeper parabola, your derivatives are going to be higher values. So you can basically take bigger steps down the parabola to get to a minima faster. So that's what the pre-processing does for you. Without the pre-processing, you might wind up with a shallow parabola that could take like a really long time to actually converge. So hopefully that answers your question. Okay, this is great. So, well, okay, so the algorithm's done running. I know what happened here. So we can see that the values for M and B are correct. These, the value, this is in that bottom left. So actually what I can do is maybe move it here. So hopefully it's a little more visible. So we can see that it's 0.0253, which is the correct value that we're aiming for in the beginning. And the B value is negative 1.1406, which again is what we were aiming for in the beginning. We predict that a video game with the Metacritic score would sell 0 games in millions, because I never updated this part of the function. So I just am still returning 0. What I need to do here is do M times critic score plus B, and that will actually generate the proper prediction. So I'm not going to run this again because it'll take a couple minutes, but we can actually look at the prediction here by basically redoing this ourselves, and to see what the prediction is. So I will, what I'll do is, this is cheating, but it's kind of anticlimactic, but I don't think you guys want to sit here and wait another couple minutes while this runs. So we'll run it this way, and we'll at least get to see what the prediction is. It's already been declared true. Okay, so this would predict, roughly like almost 900,000 video game sales if your Metacritic score is 80. So that's what our model. That's kind of what our model predicts, and that's gradient descent. That is all I have. It's a small but powerful algorithm, and now hopefully you understand a little more about how machine learning works. Again, we use gradient descent on kind of a toy problem that's like not that interesting, but variants of gradient descent are used in problems like handwriting recognition and even in GPT. The variant of gradient descent that you might be interested in looking at is something called Atom, which basically Atom just changes the way that it moves down this parabola, but all of the fundamentals are basically the same. And so you've learned a technique, or you've learned an algorithm that is used in some really cutting edge stuff that's happening these days. So hopefully you found that interesting.
Thanks for watching.